Hello, everyone. This is Professor Ma, and this is the introduction to the sections of expressions. Okay, and these are the basic things we're going to review about mathematical expressions. Okay, we're going to um, talk about what expressions are, and in particular, we're going to concentrate on polynomial expressions and rational expressions, and then some other operations that we will use throughout the course in calculus, most often. Okay. So, what are expressions? Okay, suppose here's an example. Okay, let me read it for a while. Basically, and if we have want to order pizza online and go online, every pizza is $8, and in order to deliver, and there will be $10 delivery charge. Okay, so if I order 5 pizza, it's $50, right? 5 pizza is $40 plus $10 delivery. I can make a formula out of this. If I order X pizza, then it will be A times X 10. Okay, and this is called expressions. Okay, and what do you use it for? You want to produce output, calculate what do you expect. So if I want to order 100 pizza, I type it into my order online order form. You push enter, and out pops. It's going to cost you $800 plus $10, total $810 for the 100 pizza delivered to your door. Okay, so in other words, we use expression to calculate future output, or a projected output, if you like. Okay, what will it be if I put the input into it? What the outcome will be? Okay. Expression calculate the future results. What kind of expressions that are we interested in? We are interested in given the number x, okay, depending on how many pizza you want to order. Okay, x could be some other formula measures the length of a picture. Or x can be the weight of a stone. So it could be different variables. And what do we do with these numbers that we measure? Well, if the formulas only makes up with taking the numbers you have, x, and you multiply it to some other constant like 2, or maybe you square the numbers you have, x squared, multiply over here by 3 in these formulas, and then you add them together, or subtract them together. These types of formulas are called algebraic. That is, you take the x, you do some simple operation to itself, and then you add the different types of simple operation, including dividing them. Okay, so including taking square root. So we consider all these to be algebraic. That is, take them if you take the number input, you do something you can calculate with it. With the multiplications and divisions. Okay, I'm taking this. What kind of formulas are not algebraic? Here, like log or sine of x. If you don't know what these are, that's fine, because we will talk about log and sine of x is concept of trigonometry. So in particular, in this formula, if I tell you what the number x is, it's very difficult to calculate with the number x what sine of x is going to be. I cannot take the number x and say, oh, maybe I multiply to itself, divided by 3, add 1/2 or something else, I will get the answer easily. The answer is no. So the calculation is different from the algebraic. And what kind of algebraic formula we are interested in? Okay, the most important class of algebraic formula we are called polynomials. You take the x, multiply to itself many times, multiply that by a number. Then you take the x, multiply itself many times again. Okay. And the formula arranged them in orders of how many times x is raised to a power. And these type of formulas are called polynomials. If I make a fractions out of two polynomials, one on top, on the bottom, okay, it's a fraction. By putting a number x, I get a number on top, I get a number on the bottom, I get a fraction numbers out of the outcome. So this type of fractional formula we call them rational formulas or rational expressions. Okay. What do we do? A little reviews on polynomials operations. Okay. Here it's an example of try to brief reviews on how to multiply, and in particular, these problems ask us to do two sets of multiplications, then subtract the results. So let me remind you how do we multiply these to 4. Okay, and x times x, so the 2x times x is 2x squared. Okay. 2x times 3 is plus 6x. And then this is done. Then I'm going to pick up minus 5 times x, it's minus 5x. Minus 5 times 3 is minus 15. Okay, that's the product for the first two polynomials. And I can clean this up a little bit. This is 2x plus x. This to get us x. So this is briefly how we multiply these two sets of binomial tables. Okay. The problem asks us to multiply two sets and subtract another two sets more. Okay, and in this particular example, just ask you to watch out for subtraction problem, because the product is going to be three items, and we are subtracting these products. So to be safe, you need to put parentheses or bracket around to protect that. So there will be no, it's very easy to do algebraic mistakes. Multiply it out, and then remove the bracket, change the sign, and then combine like terms. Okay. Another way to do this is you can put a minus sign into one of the parentheses and change the problem into an addition problem. Then you don't have to worry about sign changing. Okay, so these are examples of simple calculation like this. You have to watch out for subtractions. Okay. So what else we do? Polynomial factor. Okay, we did factors from last sections. So that is breaks up polynomials or write polynomials as something times something. Okay, and here are two formulas we will use them. The third degree formula we won't use it that much, but it will pop up in the future. Okay. So for example, here is a third degree formula. So basically how we factor using those formulas, the formula on the side, okay, the form. And so this is for third degree formula, example of third degree formula. Okay. What do we want to factor polynomials? And here are a couple of examples of which we're going to use in the futures, again, based on factor the polynomial, the factor. Okay. It's easy to calculate. Okay. If I say put x equal to -2 into this formula, so calculate. So I'm going to replace x by -2, everywhere and calculate the outcome. The easier way to do it is actually factor first. Okay. In other words, instead of putting -2 into these formulas, into these places in the x, which you have to multiply -2 to itself 3 times, it's a lot more convenient to put into here. The x, put a -2 over there. Okay. The calculation via the blue lines, putting into the factor form, is a lot faster calculations. It's going to be -2 times 3 number multiplied, it's going to be -4. The other way, you have to calculate -2 cube and all that things. Imagine what happens if it's a 10th degree formula. And have 10 little parentheses. You just have to calculate each one, multiply them together. 10 numbers, you will have your answer if you factor it. But if you don't, you have to take the number, multiply to itself 10 times and 9 times, 8 times. So these are similar procedures to the minus one. So it's sometimes it's easy. So it's easy if you try to evaluate using the factor form. Another thing, it's easier to check the output of the sign of the output. Sometimes I don't need to calculate what the number will come out. All I want to know is if I plug in a number, if the outcome is going to be a positive or negative outcome. Put -3/2 in here. There's a fraction, and you have to calculate fraction -3/2 square, stuff like that. And again, I said, no, let's not do that. Let's use a factor form. We're going to take the -3/2, put it in here. And then the second thing is we're going to be lazy about it. I'm not going to calculate what the numbers of each parenthesis will come. All I'm going to is to observe the parenthesis whether we wind up to be a positive or negative. -3/2 -3, that's going to be negative in the first parenthesis. Okay, they're going to have a negative result. Okay, -3/2 plus 1, and that's going to be a negative result also. So you're going to have two negative numbers multiplied, so the end's positive. Okay. So, and this trick we will use soon, okay, to produce something called a sign chart. And so we will come back to these tricks of determining the output of the sign. What else do we, okay, now let's come back to the rational expression, the fractional ones, okay. Again, we can factor fractional. What do you mean by factor? It means the top is factor, the bottom is factor, the little sets of parentheses as much as possible. So here's the factor form, okay, of the same formula. And what is the factor form good for? Well, you can probably already see there is a identical factors component in the factor. And we can cancel that. He said, what do you can cancel that? Well, here, if I were to think of any numbers, think of your favorite number, 5. Yeah, there we go. Let me put x to the 5 into this formula, okay? But instead, I'm going to put in that form. The portion of 5 minus 1, 5 minus 1, it's going to be 4 divided by 4. 4 divided by 4 is 1. Okay. In other words, this is going to be divided into 1, and the 1 is going to multiply the other part of the formula. So it's irrelevant in the calculation. It doesn't matter if I were to put 6 in there, I will get 5 over 5. Then again, they cancel. So we can reduce. Okay. So the root is this root. If you have that components x over x times the rest of the fractions, then whatever x you put in there, x over x is 1, you can cancel, we call it cancel, reduce it. Okay, so this reduce, the x minus 1 may be canceled out. A lot of time in mathematics, we just say, this cross this, and then put a 1, just run as a 1 there if you want to. Okay. Then the result is that. How do we multiply fractions? Just like we multiply numbers. Again, when we multiply or divide, how do we divide? We flip over and multiply. Then how do we multiply? Since both multiply and divide is a multiplication problem. So how do we multiply? Well, we don't really multiply. We factor and clean up. We don't really multiply one thing and one. We rarely expand the multiplication. When the problem is a multiply, actually it's a simplification or divide. In other words, first write as multiplication problem. Next, do not multiply. Factor actually break up into little parts. Okay, and then you cancel. Then you look over the factor that are the same factors and then cross things out. Notice this one, x minus 3 and 3 minus x. Cancel is to be -1. Okay? Think about these. Again, if I want to put a 5 in there, I mean, let's use the same old x equal to 5, see what happens. I put 5 in there, 5 minus 3 is 2, 3 minus 5 is -2, so I'll have 2 divided by -2. But 2 divided by -2 is going to be a minus sign. So it doesn't matter what number I put in there, these two parentheses will cancel to be -1. Hence, these cancel, and the residue is a -1 multiplied to the rest of the problem, whatever the rest of the problem turns out. Okay, but these two collapse into -1. Then I clean up what we have, and that's the result. That's how we multiply or divide fractions. What else we do with fractions? Occasionally we'll give a complex fraction. Oh, no. So let's talk about as subtract. We're going to use the least common denominator trick to add subtract fractions. Like for instance, I'm going to use these tricks for adding these 3 fractional numbers. Okay, we will need a least common denominator. If you don't understand how to get least common denominator, go look into 125S, the class before this, and look in the fractional expression. That chapters that there's a least common denominators, and learn how to extract that. Okay. For instance, here least common denominator is 48. Okay. Why? Because I can take 48 and multiply to any of these 3 parties. It will get rid of the denominator. 48 times 7 twelfths. 12 going to 48 is 4, and the answer is 28. 48 times 5 8. 8 goes into 48 6 times. 6 times 5 is 30. 48 times individually, 9 16. Cancel 3. The answer is 27. 48 is the smallest number that will remove all the denominator of the other 3 when you multiply through them. Okay, and what am I going to use? How am I going to use the 48? I pull the following tricks. I multiply by 48, then divide by 48. In other words, this is a 1. Okay, so I haven't done anything, but I write a 1 as 48 over 48 as 2 parts. But then when the actual multiplication happens, I multiply the top 48 to the problem and leave the bottom one below. So everything now is over 48. Okay. The bottom, the top, now I'm going to multiply. Okay. Distribute. 48 times 7 12, cancel. Left with 4. Cancel left with 8, cancel left with 3, and that's those individual products, 3 of them, and they are in the numerator over the 48 on the bottom, and so that's the answer. We're going to pull the same tricks now with fractional formulas. Okay. First, I need to make up the polynomials or the 2 binomials that will cancel the denominators. Okay. I factor them, and this is the least common denominator. That will cancel when I multiply to this and multiply to that will cancel this. There will be something left over, of course, but that's what we're going to calculate with. Take the problem, multiply by the LCD over the LCD, 48 over the 48. Then I multiply the top numerator across. Cancel. Y minus 1 cancel with y minus 1, y plus 2 cancel y plus 2. The leftover is y plus 3. So put a y plus 3, which is going to multiply to 2y minus 1. But I'll do the next steps. And then carry over to the next one. Okay. And then after the denominator dropped out, I have these problems of of subtractions, then I subtract and expand it subtracts, and then put the answer together. Okay. So this is how we add subtract fractions. Now what else we do with the least common denominator? That the number that 48, or we removed all the denominator, and here's another way we use the least common denominator. Clean up complex fractions. Oh. Okay. Multiply, here is the common denominator is 12 of all the fractions involved. So I'm going to multiply the top by 12 and multiply the bottom by 12, which is what? Then I multiply across. The 12 will remove all the individual denominators. So the quadruple level suddenly collapse into bi-level. Okay, from 4 levels now into 2 levels. Okay, then I simplify 2 level like a regular fraction. And this can be done with fractional formula like this. Okay, so I'd like to read this particular one to see how the simplification works out. Using the common denominator x minus h, x plus h, and I multiply the problem of by the common denominator x minus h, x plus h. To do what? To remove these individual denominators, which wind up to be these. Okay. So yeah, so I'll leave it to you to read through these algebraic versions of simplifying complex ones. Then lastly, there's a little trick that we will use later on, is using the conjugate multiplication to do something we call rationalizing the square roots. Okay. In particular, these two x plus y and x minus y are called conjugates. And the product is very nice. Okay. And we use these to do something called, in the titles here, instruction, rationalize the numerator. The numerator refers to this. What do you mean rationalize? It means remove the square root. The square root is not a rational number. It's not a fraction. Square root number is not a fraction. So change into a regular without square root. We say, well, how do you do that? I mean, put the square root somewhere else, just not on the top. How do we do that? Okay. Oh, use the conjugates. Because the conjugates multiply the square, you will have the square of the square root subtracting, and it will remove the square root from the top. And in this case, you run out h, and the h will cancel out, and then this is the answer. So in other words, this formula, in a sense, is this formula, same formula, except square root at different places. What's the point? It turns out, yeah, this is a very good example later on when we're going to calculus, doing derivatives. Okay, so this is an important trick in, for doing that algebra of the derivatives. Okay, that's it. Okay, and have a good day and do the homework, and see you next time. Bye bye. Okay. Oh, bye bye.